So now we're going to go through question 3. Part A says that quantum mechanical problems are often treated via a formalism called matrix mechanics, where quantum mechanical states are defined in an n-dimensional vector space. So these first few questions are going to be asking us, do we recall our basic knowledge of linear algebra? So part I says, in 1 or 2 sentences, explain what basis is for a vector space, and in particular talk about linear independence. Okay, so we ought to fix ourselves a vector space. So let V be an n-dimensional vector space. And I won't specify exactly what field it is over yet. That doesn't matter for this question. So, what is a basis? We say a set, we'll call it curly B, and it's going to consist of these BK guys running from k equals 1 up to n, is a basis for V if, now we need 2 properties to hold. B spans V, and B should be linearly independent. Now what do these mean in particular? So for B to span V means that for every vector V in the vector space, we should always be able to find some constants, we'll call them alpha k, such that V is a sum of these alpha k's bk's, okay, from k equals 1 up to n. Means that we can always write every single vector in our vector space as some sort of linear combination of the basis vectors. Okay, that's super important. But equally important is the property that they should be linearly independent. So what does this mean? This means that whenever you have the equality, say alpha 1 b1 plus alpha 2 b2 plus all the way up to alpha n bn, just adding just some linear combination of the basis vectors being equal to 0, well, if that's the case, then each one of the coefficients, alpha 2, alpha n, should be equal to 0. Basically what this means is that there should be no non-trivial way of writing any one basis vector in terms of the others. Okay, that means linearly independent set. Okay, now we move on to part 2. Part 2 says that we generally like our bases in quantum mechanics to be orthonormal. There are 2 requirements for a basis to be orthonormal. What are they? So, what we need to do in order to answer this question is to fix an inner product on V. We'll call it these brackets here. We need this to talk about orthogonality. So, basis B of V is said to be orthonormal if, okay, so we've got this property here that the inner product, sorry, I'll use the notation B, Bi, Bj is equal to 0 if I is not equal to j, and 1 if I equals j. Okay, these are our 2 properties. This 0 if I is not equal to j, and some non-zero thing if I is equal to j. This is the orthogonality condition. and this being in particular equal to 1 when I equals j is the normality part of the orthonormal basis condition. So now we're going to move on to 3. A fellow student makes the following statement. When a linear operator L operates on one of its eigenvectors, the resulting vector is parallel or anti-parallel to that particular eigenvector. Is this statement correct? Yes, this statement is correct. If we have a linear operator L and an eigenvector, which is this ket lambda, if it's an eigenvector, means that there's some sort of non-zero constant mu that when you act L on the eigenvector, you get mu times that eigenvector back. We might like to think of the following picture. The set of axes is meant to denote our vector space. Now let's consider this arrow to represent our vector v. Okay, when A acts on this vector v, if it is an eigenvector, all we will do is just effectively scale it. Okay? Because it's just a constant multiplied by that same vector. Okay? So one particular case is that it scales outward like that, or it may even scale in the opposite direction. These are the parallel and anti-parallel conditions to the original vector. Okay? So one might like to draw a diagram and write a few sentences explaining the diagram the way I've spoken it, and that would be sufficient for this question. Okay, so now let's go on to part 4. We have a particular linear operator L, and we're asked to find the 2 eigenvalues of it. So we know to find the eigenvalues, you want to set up a polynomial determinant of L minus some lambda times the identity matrix, and set that equal to 0. Okay, this is going to give you your eigenvalues. Okay, so for this particular case, when we have L as it is, we're looking for the determinant of this particular matrix here. And setting that equal to 0. Okay, so if we go and actually compute this determinant and play around with algebra a little bit, you'll actually find this factorized quadratic form here, which tells us, therefore, lambda equals minus 2 and lambda equals minus 3 are eigenvalues of L. Okay, now find the corresponding eigenvectors. This is a relatively simple process. We just take the matrix that we had formed, L minus lambda I, and plug in each particular eigenvalue and go and row reduce this matrix. Okay, so for the first example, maybe we take lambda equals minus 2. Okay, so the matrix that we get when we plug in lambda equals minus 2 is minus 1 minus minus 2, so that's a plus, 2 minus 1, and minus 4 minus minus 2 again, so that's minus 4 plus 2, and that's equal to the matrix 1 minus 1, 2 minus 2. Okay, and quite clearly this has the same solution set as this matrix here. which means that the eigenvector, call it V1, corresponding to this eigenvalue, is just going to be 1, 1. Okay, let's do the same thing for the lambda equals -3 case. We've got the matrix now -1 minus -3, so +3, -1, 2, and -4 minus -3, so +3, which is then equal to 2 minus 1, 2, and -1. Again, clearly has the same solution set as 2 minus 1, 0, 0. And we can write down the second eigenvector as 1 and 2, like that there. Okay, so part 6 says, quickly use our answers in the previous two parts to demonstrate that part 3 occurs. And part 3, if you recall, was that acting a linear operator on one of its eigenvectors produces a vector that is parallel or anti-parallel to that original vector. So let's take, say, V1, for example, and act L on V1. So recall, L was this matrix -1, -1, 2, -4. And we computed V1 to be 1, 1. So let's just matrix multiply. What do we get? Get -1, -1, so that's -2, and 2, -4. So that's also -2. And so that is -2, 1, 1. So what is -2 times 1, 1? That's just a vector anti-parallel and twice the length of V1. So this demonstrates what we said in part 3. Okay? So let's move on to part B. So observables in quantum mechanics are represented by Hermitian operators. Okay? Part I asks, what is the one key requirement of observables that require the operators to be strictly Hermitian? So, what is the one desirable feature of observables that we need that tell us that you should take Hermitian operators as your observables? And it's the fact that we can only measure real numbers. Can only measure real numbers. And if you recall, the eigenvalues of an operator, the eigenvalues of an observable, are those particular outcomes that we would expect to measure. So, eigenvalues correspond to kind of results of an observable. We have to restrict the particular eigenvalues that a linear operator can take. We must require that they are real numbers, because we can only measure real numbers. So that is eigenvalues of observables must be real. Now, how do we guarantee this? It's a theorem of linear algebra that says if you take a linear operator and you take it to be self-adjoint or Hermitian, then the eigenvalues of that operator are always real numbers. So this is why we take our operators, our observables in quantum mechanics, to be Hermitian linear operators. It's because we are guaranteed real eigenvalues. Okay? Hermitian operators guarantee real eigenvalues. Okay. So let's go on to question 2 now. Probability is an observable. Is this statement true or false? This statement is false. Okay. As we've identified, observables in quantum mechanics are special types of linear operators from special vector spaces. Okay. Probability, on the other hand, is a map from some sort of space of events into the closed interval 0, 1. Moreover, when we talk about probability in quantum mechanics, we're talking about what is the likelihood that a measurement yields particular values of an observable. And so in that way, if probability were itself an observable, it would kind of be circular to have defined it that way. So you might like to write 1 or 2 sentences explaining what I've just said there. Probability is not an observable. Okay. Part 3. Let's consider this operator L again. Is L Hermitian? Okay, so let's think about this for a second. Even though L had real eigenvalues, it still might not be Hermitian. Okay, there's an implication one way but not the other way. So how do we know definitively? Well, recall what it meant to be Hermitian. A matrix was Hermitian if it is self-adjoint. What is its adjoint? Its adjoint is its conjugate transpose. So let's take the conjugate transpose of L. That we typically denote by this dagger in quantum mechanics. And the conjugate transpose, just write this matrix again. The conjugate transpose is effectively just given by the transpose in this case because all the entries are real. But this matrix here is definitely not equal to L. And so this matrix is not self-adjoint, it's not Hermitian, it does not constitute an observable in quantum mechanics, even though its eigenvalues are real. Okay, part C. I want to consider a 3-dimensional vector space spanned by an orthonormal basis, given by these 3 ket vectors right there. 2 possible quantum states are given, as alpha and beta there, and we want to construct the corresponding bra vectors, which are those corresponding vectors in the dual space to our vector space, in terms of the dual basis 1, 2, and 3. Okay, so we may like to just write down a few things first. What is this vector space? This vector space is the complex span of these symbols here. 1, 2, 3. In quantum mechanics, we like to take complex vector spaces in concrete examples. Okay, so now we should also maybe write down what the dual basis condition was, just if you need to recall. So this bra vector here is, or this set of bra vectors indexed by I will be dual to the set of ket vectors indexed by j here, if this is equal to delta ij, the Kronecker delta. So 1 if I equals j and 0 otherwise. Okay? So it's actually quite easy to construct alpha and beta in terms of the dual basis. If we think of column vectors as being 1 by 3 matrices, then we can very easily take adjoints of it, conjugate transposes, as we talked about in the previous question. And that is exactly what these dual vectors here are going to be. simply just the matrix adjoints, the conjugate transposes of. Okay, so in that way, the bra alpha is now minus I, the bra 1, minus because we need to take the complex conjugate, minus 2, 2, plus I, 3. Okay, and similarly for beta, it's going to be minus I, 1, plus 2, 3. In the second part, we want to find the inner product between alpha and beta and alpha and confirm that these two are complex conjugates of each other. Okay. Now, what we like to do is to write the bra and the ket next to each other. Okay. So here we're talking about the bra alpha, as we just wrote down before, minus I, 1, minus 2, 2, plus I, 3. And then we write next to it the ket beta. Now the ket beta was I, 1, plus 2, 3. Okay, so we notice because these vectors here, vectors and dual vectors, are orthonormal, it suffices to only compute the corresponding pairs. By that I mean the only time we're going to get non-zero terms in this is when 1 acts on 1 and when 3 acts on 3. Okay, so we get minus I times I in a product of 1 and 1. And the only other non-zero term is going to be 2I, 3 and 3. And this gets us 1 plus 2I. Okay. Now we should also compute this the other way around. So we'll do the exact same thing. Get now minus I, 1 plus 2, 3, because that is the bra corresponding to beta. And then the ket corresponding to alpha is I, 1, minus 2, 2, minus I, 3. And I'll spare you the details. We write this out again, and we get exactly 1 minus 2I. Okay, and so clearly, take alpha, beta, complex conjugate of that is beta alpha, as required. Question 3 concerns what you might know as alpha products or tensor products. So if you don't remember, let me just recall for you a definition. The outer product of these two vectors here is going to be given by the matrix, which will be fix the first entry of alpha, then multiply through by the other entries of beta. Okay. Now, if we are thinking about this as beta as the bra, we write it like this. But if we think about it as beta as the ket, we might just like to be careful here and just label these as the complex conjugate. So I might write down here, we take outer product of alpha equals I1 minus 2, 2 minus I3 and beta equals I1 plus 2, 3, just so we don't get confused. Okay, and then you repeat this process. Alpha 2, beta 2 bar, 3, beta 3 bar, alpha 3 beta 1 bar, alpha 3 beta 2 bar, and alpha 3 beta 3 bar. Okay, so let's compute this for this example here. Okay, so O hat is then going to be, okay, fix the first element of alpha, that's I in this basis, then multiply it by the corresponding complex conjugated coefficients of beta. So we've got then I times, now minus I, okay, so that's just 1. Then we've got I times, now it's 0, because we've actually got here 0, lots of 2. And I times 2, that's 2I. We go to the second coefficient of alpha, that's minus 2. Minus 2 times minus I, that's 2I. Minus 2 times 0, again it's 0. And minus 2 times 2 is minus 4. Now we fix the last guy. Minus I times minus I is minus 1. Minus I times 0, of course, is 0. And minus I times 2 is minus 2I. And that is the outer product of those two vectors in this basis. Okay, so now let's move on to part 4. Is alpha properly normalized? And if not, obtain the normalized form for alpha. So what does it mean for a vector to be normalized? Well, we say a vector is normalized if its norm or size is 1. Okay, so is alpha, alpha was the vector given by I1 minus 2, 2 minus I3. Is this normalized? No, it's not. How do we see this? Well, we compute the inner product of alpha with itself. Okay, so this is going to be minus I times I, minus 2 times minus 2, minus I times I. Okay, so that's going to be 1 plus 4 plus 1. That's equal to 6. Okay, now the size of alpha, the norm, is the square root of this inner product here. So it's square root 6 is its size. So how do we obtain a vector that is parallel with alpha but has size 1? Well, we just take alpha and define a new vector, we'll call it alpha bar, which is just alpha but divided by the size of alpha. Okay, so that is I on root 6, 1, 2 on root 6, 2 minus I root 6, 3. Now the inner product of alpha bar with itself is going to be 1. So this is a normalized form for alpha. And we know that normalized vectors, vectors with size 1, are states in quantum mechanics. So if we consider part 5, we prepare a quantum system in the state alpha. Now by alpha here we mean alpha bar. It must have norm 1 to be a quantum state. So then we go have lunch, come back and perform a measurement. So what is the probability that we obtain the outcome 2 after having measured our state? Okay, so the important thing about this question is not so much that we go have lunch, but that we've left the state, left the system for some time. Now time evolution in quantum mechanics is given by unitary operators. What this means in particular is that probabilities don't change over time. If we set up a system in the state alpha, then it remains in the state alpha, and all the probabilities of measurement don't change with time. So what we do is just look at Born's postulate again. That was that the probability that we measure the state 2 when we have set up our system in state alpha, or alpha bar as I have it above, is just given by this inner product, then you take the modulus, then you square it. Okay, so this is just the modulus squared of the coefficient of 2, which is 2 on root 6, okay, which is 4 on 6. Okay, so that is the probability that when we measure our system, we obtain the outcome 2. So finally, suppose that without otherwise perturbing the system, we go have dinner. Now this is after having assumed that we do actually measure the system in the state 2. So what that means is that the wave function has collapsed into this state 2, and the system is now in the state 2. Okay? So once we've made this measurement, we go have dinner. Then we come back and remeasure. What's the probability that we measure the state of the system being 1? What is probability that we now measure 1? Well, if we go and look at Born's postulate again, this probability is given by this here. Okay, but because these bra vectors indexed by these natural numbers 1, 2, 3 form an orthonormal basis for our system, this inner product is 0. Given the fact that our system is in state 2, it's not a superposition of any other guys, the probability that we measure a state orthogonal to it is 0. Okay, so that concludes question 3.